Okay, in this example, I just want to give you an example that'll include a lot of the aspects of a problem you might see on the exam. Okay, we have a consultant that proposes a seminar. They're going to fill out an effective delegation scale. And if the scores are less than 16, we'll hire the consultant. So we want to show in our research hypothesis that the population mean is less than 16, because if we can show that, we'll hire the consultant. HO is mu equal to 16. Of course, you could put mu greater than or equal to 16 as well. But we're going to use mu equal to 16. That's what we'll have in our sampling distribution. So we'll take a look first at this from the vantage point of the p-value. So we have a random sample of 25 managers and the scores for each. And I've already calculated the sample mean. It's 15.08. Let's say that on basis of past experience, we know the population standard deviation is 4. So we want to know, is the population mean less than 16? So the first thing we'll do is we'll sketch the sampling distribution and shade in the area below the observed statistics. We're going to go below because it's a one-tailed lower test. Look at your research hypothesis. So we have the sampling distribution here. Note that it has X bar on the axis, mean of 16, and a standard error. We took the standard deviation of 4 divided by the square root of n to get 0.8. And then, of course, our area shaded in is the area below 15.08, which is the statistic we computed from that random sample of 25 managers. Now we're going to compute the probability, which is the p-value, the probability of obtaining a statistic this far from the hypothesized mean, under the assumption that the mean proposed in the null hypothesis is true. So we calculate our z-test, get the distance from the mean, x bar minus the hypothesized mean, or 15.08 minus 16, and divide by the standard error, which is 0.8. So we're a little more than one standard error below the mean, minus 1.15. If you use your z-table, you'll find an area of 3749. Of course, that's from the mean to this point, or from 15.08 to 16. But we want below that, so we'll subtract that from 0.5, and we'll get a value of 0.1251. And that is our p-value. So here's our interpretation of the p-value. If the true population mean is 16, that's what we have in HO, then the probability of obtaining a statistic this far or further, consistent with HR, so we're saying below 16, is 12.51. So even though the sample mean is less than 16, we would get a sample mean that's lower or lower about 12.5% of the time. Therefore, the null hypothesis is plausible and will not be rejected. So we can't say that the population mean is less than 16. So we don't need to hire the consultant. Let's keep the money and leave our managers alone. So here's one way to answer the question, how can you use statistics? Before you implement the latest Flavor of the Month training program, make sure you really need it. So now let's take a look at the critical value approach. We're going to formulate the hypothesis, which we've already done. HR is mu less than 16, then HO equal to 16. Then we're going to have a decision rule. Our decision rule, we're using a 0.05 level of significance. we're going to reject HO if z-test is less than minus 1.645. Remember, we have a one-tailed lower test. So using the table I gave you in class, you just go to one-tailed, 0.05, and go down to the bottom, you'll see 1.645. It's less than minus. That's consistent with our research hypothesis, mu less than 16. You could also look back at that sampling distribution and see that we're looking at the lower tail. We're going to compute the test statistic, z-test. Actually computed this in the last part. 15.08 minus 16 over 0.8 is minus 1.15. So we fail to reject HO because minus 1.15 is not less than minus 1.645. Our conclusion is the population mean could be 16. Actually, it could be a little more than that. But we're just testing 16 at this point. So our implication is don't implement the training program. I'll go ahead and tell you now, on the exam this semester, it's probably going to be more likely that I'll use the critical value before the p-value approach, simply because we've got the z-test calculated here to be minus 1.15, and then you can use that in the next section to calculate your p-value. It's really no philosophical reason for it, just a matter of making it hopefully a little more easy for you. Then the confidence interval approach, take the statistic, x bar, plus or minus the confidence coefficient, which in this case is a z, times the standard error. We're doing I think it was a 90% confidence interval in this case, 1.645 times 0.8. So that goes from 13.76 to 16.4. Remember that we have to evaluate confidence intervals by looking at the entire interval. I'm going to go back here. Well, before I say what I just put up on the screen over here, for example, with this interval 13.76 to 16.4, we can conclude that the population mean is less than 17. We can conclude that it's greater than 13, but we can't conclude that it's greater than 14 because the interval includes numbers that are less than or equal to 14. Nor can we conclude that it's less than 16.39. What we're saying with this interval is that the population mean is somewhere in the interval. Okay, a more theoretical explanation is that if we repeatedly constructed intervals like this, about 95% of intervals would include the population mean, and 5% would not. What I want to emphasize here with that 5% would not is the idea I've been kind of getting at throughout the course, and that is that you're not going to have certainty when we construct and interpret this interval. There is a chance you're wrong. We can be confident 95% of the intervals will conclude. We can be confident 95% of those intervals will contain the true population mean, but let's keep in mind that 5% won't. There's always a chance that we will be incorrect. If 95% is unacceptable to you, then make a 99% confidence interval. There's a trade-off there between the width of the interval and then the chance for an error.